Okay, now we finished up to 8. We're going to go into virtual memory, which is a very important topic. A lot of this is going to seem familiar because we've hinted at a lot of this during paging, but virtual memory is going to really clean it up about how the operating system actually handles all these pages and different processes together. Also, preemptive apology, I gave you homework that actually last time does rely on the information in Chapter 9. So if certain parts of it didn't make sense, like what I meant by LRU and FIFO, we're going to cover that today. So be ready. You'll be good. Virtual memory, we're going to cover all these topics. Great, thanks. Yes, virtual memory is good. All right. Separation of user logical memory from physical. Why is this desirable? Why do we want to do this?
So that you can separate out the kernel and the operating system and make sure that they don't get overwritten.
True. So does provide a way to separate the kernel and the user programs.
So that memory addresses can be separated from physical. They're relative to the program instead of set to the hardware.
Right. So now, yeah, that's the point of that's what virtual memory does, is that they process only sees its own memory space. And why? And it does not tie to any physical hardware. Why is that desirable? What's a good use case for why that would be helpful?
Because if you design the program on one computer and it sees 0x83, that might not be the same memory. That memory space might not be available on another set of hardware.
All right. Yeah. So there might be that for platform. Yeah, that's a good one. That's a good platform independence. Another really classic example here is, what if your memory can only support 6 of the 8 processes you want to run? Virtual memory gives you a way to be able to actually run all 8 of them, but swapping them in and out as needed from the hard drive. Okay. There's 2 different ways to do it: demand paging, which is in general the way it's done, and then demand segmentation. All right, virtual memory that's larger than physical memory. This is very common. You may have a very long virtual memory, but your physical memories, notice that's only a subsection. And then the hard drive is used to basically pick up the slack of any memory that's not being used. Virtual address space. This is how programs view memory. This is how we've been taught, or how I probably taught y'all in OOP. And if you listen carefully, I said for the time being, just think of memory this way. That's because I didn't have time to teach you virtual memory in OOP or Java. But even when you write your program, when the compiler spits out the code, this is how it views memory. It's not actually taking into account virtual memory at the time. It's spitting out code that actually looks like this. So it was perfectly fine for me to say that in OOP. I'd say shared library using virtual memory. Okay, so yeah, if you have a shared library, when you reference something in this stack, it actually goes to the same piece of physical memory as in another process, which is another nice feature of virtual memory. All right, demand paging. So what demand paging is only bring a page into memory when it's needed. So your program initially says, all right, let's go ahead and start up. And the operating system says, okay, you're running. I just haven't loaded any of your memory into main memory. It's all on disk. And I'm only going to load it in when it's needed. So what's some benefits here? Well, since you're not loading in the whole program, maybe you're not going to use all of it. So that's less I/O. Hopefully less memory is needed as well. So now you can probably support more processes in flight in main memory. Faster response, because I don't load your program into memory. I just say, yes, you're ready, go. And well, more users, really more programs running, I think is a better way of putting that. So if a page is needed, a reference to it, and then if it's an invalid reference, once they reference something, if it's not valid, or it's not in memory, bring it to memory. Invalid reference, of course, abort. All right, what does this imply about every time, if we're using demand paging, what does this imply about your program? What's the first thing that happens when your program runs? page fault. Why is that?
Because nothing's.
Nothing's. So in demand paging, when you run a program, basically one of the first things that happen is you get a page fault because your program's not in memory yet. So then the operating system, of course, then loads it in. That is how it's done. Lazy swapper, don't swap a page into memory unless it will be needed. So this is, unless it will be needed, right. So that's the same thing. That's what we're talking about with demand paging. All right, swapper that deals with pages is called a pager. I guess y'all don't have the other definition of pager anymore. A little thing put on the side, get paged. And then told you, I always thought that was funny. It told you the phone number to dial, so you'd have to leave, find a payphone, and then dial that number. Anyways. All right, here's another picture. This is a great chapter. They're giving you plenty of pictures. So program A might be, actually it could be a bunch of different sections, but we'll just say it's 4, 5, 6, 7 on the disk. So I will say that we need to transfer page memory to a contiguous disk. So maybe program A, this part of program A is too big and we need to swap in program B. I don't know why we're not swapping it to the same memory space, but the idea is you swap one out and then swap the other one in. And all programs at least reside on the hard disk because that's where you start them. All right, again, we're going to have valid and invalid bits. Valid means that it is actually in memory, while invalid would say it's not in memory, and that would cause a page fault. So if it is valid, go ahead and get it. So yeah, this could be an example. Usually at the top is where you actually have valid pages, and then moving on down where you might have something invalid. So if it's invalid, equals page fault. Oh, good. Good example here. If I try and reference A, 0, it's valid. It happens to be at 4, so we jump over. But if I try and reference B, it's not in the 1, you jump to 1, it's currently invalid, which means that the operating system would need to bring that into memory and then store where the base is inside the page table. We good so far? There a reference to a page that's not actually in there. It's called a page fault. So it looks at the table to decide, first off, is this reference invalid? Are you trying to write to the kernel? If so, abort. Otherwise, it's just not in memory. If it's not in memory, find an empty frame in memory, or empty page in memory. Swap the page into a frame. Reset the table, set the valid bit to D, and then restart the instruction that caused the fault, aka do the context switch back to the process. I don't know what this picture is trying to tell you. So we'll go over here, because this makes more sense. One, reference load this with the page fault. It happens to be invalid. Trap, which means that the operating system has to do a context switch, take all the registers from the process, store it out in memory, get the kernel to come back in, find, oh wait, where's the page? It's currently in the backing store. Note that the page might be somewhere else, but for now we're just going to say it's in the hard drive. Get on the hard drive, bring it in. Notice this requires I/O, so now the process is going to be blocking due to I/O as it tries to get the memory in. Bring the missing page into physical memory, reset the page table, basically update the page table to have the proper index. Now it's a valid bit. Then context switch back with the actual process and start running. So the big question here is, how long does this take? Short, fast, or slow? Slow. So let's go ahead and look at the effective access time. Page fault rate from 0 to 1, aka the percentage. 0 means no page faults, which would be great. 1, every reference is a fault, which would be terrible. Alright, so 1 minus P times memory access, that's if there is no page faults. And then that's the percentage of no page faults, 1 minus P. And then P is, of course, your percentage of page fault. Page fault overhead, swap page out, swap page in, plus the restart overhead. Now, what we have to understand is maybe memory access time could be 200 nanoseconds. That's probably a good estimate. Average page fault service time is 8 milliseconds. That's actually pretty good. If that is truly, well, on a spinning disk, that'd be really fast. On a solid state, that's probably slow. But we'll say with the standard spinning disk, you get 8 milliseconds, which is great. If you actually multiply this out, well, 200 times whatever 1 minus p is, but now p times, 8 milliseconds. In other words, if one access of 1,000 causes a page fault, then the EAT is 8.2 microseconds, which means a slowdown of a factor of 40. So it's not just, page faults aren't just slow, they're incredibly slow, terribly slow. Something that needs to be avoided. Because even if you have 0.1% page faults, your program slowed down by a factor of 40. Everyone following me so far? We're good? Page faults bad?
Why did the 8 million milliseconds go down by 200?
Oh, because of math? No, I'm sorry. Remember our formula, 1 minus p is the percentage that are actually memory reference, and we're saying that's times 200 because that's 200 nanoseconds, and then it's plus p times 8 milliseconds, the percentage of page faults minus, times 8 milliseconds. 8 milliseconds is 8 million nanoseconds, so if you actually multiply, let's see what they did here. That's interesting. What happened here? They dropped a parenthesis. Well, there should be a parenthesis right here. And so 200 would be right here minus 200p, right? And then what they do? So that's 200 minus 200p, and this is p times 8 million. So then they went ahead and subtracted the 200 from over here.
Oh, okay.
Yeah, that's what. That missing parenthesis there threw me off as well when I looked at it. Okay, and then so that factor does
Why is
decrease.
that million?
8 million, because 8 milliseconds is equal to 8 million nanoseconds.
Yeah, okay.
Yeah, the trick
They
here
converted
is,
everything to nanoseconds.
yeah, the reason why this is so terrible is you're going just orders of magnitude difference, right? From a page fault to a standard memory reference.
I didn't realize they put everything in nanoseconds.
Yeah. And of course, this 200 is probably even less if we're using a caching system, which again makes page faults even more terrible. Okay, so we're going to put that in the back of our mind for now. That page faults are terrible. And the book, fortunately this chapter kind of jumps around a lot, so switch gears again. We're going to talk about process creation. And right now the big thing to keep in mind is the copy on write, which is always one of my favorite acronyms. And then we'll talk about memory map files later. So copy on write, or COW, allows both the parent and the child process to initially share the same pages in memory, and it only copies once one of the processes writes to it. So you share it until someone writes to it, and then it's copy on the write. Basically, you're delaying actually copying the memory out until it's actually needed. Why is this beneficial?
So that you don't copy memory if you don't need to.
If you don't need to, right. So you have better utilization of memory. Program's also faster because you're not running all those copy instructions. Here's a picture. See, process 1, process 2, they're forked, let's say. And so the operating system will actually have the physical memory shared until someone decides to write to it. Maybe process 2 wrote to it. Or no, we'll say process 1 write to it because it's copy on write. So that means the operating system will make a copy of that memory for process 1, and then it can write to it. But notice it's still sharing A and B, since we're using paging.
The operating system does this, we don't have to worry about it.
You are correct. Well, unless you're writing the operating system, right? Right. Yeah, so this is all handled in the background.
Is this a Windows feature, a Linux feature, an all feature?
Anyone that supports virtual memory is going to have, oh, okay. When you support virtual memory, if you have a copy on write memory system, this is how it works. You don't have to, because you could, when you fork the process, literally copy the entire physical memory out. And some older operating systems did that. I haven't looked at Windows' code, but I'd be surprised if Windows did not do it this way. This is really is a common, good way to go about it. Great question. Any others?
Are we able to ignore that?
What do you mean ignore that?
So like say we're writing a program and when we load the program or we fork something, we want it to copy all the memory because we know we're going to write it all anyway, so just copy it all up front.
There's probably a flag you could send to fork to tell it to copy everything over if you wanted to. But I mean, the operating system's handling this in the background. I doubt you're going to get much of a performance improvement. I would only suspect a performance decrease by specifying that. But I'm sure
I mean,
Linux.
like well, like programs nowadays, they usually load first, and then they act, right?
Yeah.
So the same kind of difference. Instead of going into your program, load here, load here, load here. I know I'm going to need those loads anyways.
Do
I'll
them
just
up front.
load it all up at the front end.
Right.
That way it can just write when it needs to.
Yeah. Yeah. Guess I'm not quite understanding what performance improvement you're looking for. What I'm saying is I don't see the. I mean, it's good to
The
load
time
it.
to copy.
Right. It's good to load everything first.
Instead of having it in the middle of the process.
Right. You want to front load that, of course, and then the operating system will take care of it for you from there. Yeah. Because these are just, each process has its own logical address. It's not actually making any physical differences until a copy on write occurs. So I think that's answering your implied question. Or sure? All right. Any other good questions? Matt? All right. Okay, here we go. What happens if there is no free frame? There are no free frames. There are no free frames available.
We wait.
We wait until a process. What if all the processes want memory and they're trying to access each other's memory? We would then
preempt
have.
them.
Yes, but they would still be using that memory, right? So you'd have starvation. We need to basically.
No, we tell them, write this out to disk, we're taking this from you.
Right, so that's page replacement. Right here.
Okay, that's what I was calling preemption.
Yeah, uh-huh.
We told that process, you're done with this, write it out to disk, we're gonna take it.
Sure, okay, yes. Except the difference is you're not preempting the process, you're preempting the memory space.
Okay.
And you usually don't use that word on memory. I'm just,
Okay.
right, I'm just pointing that out. I'm not saying you're,
I'm
I'm not saying you're,
I'm not gonna make
I'm not
myself
saying
sound
you're
stupid.
completely wrong. Just mostly. So,
Good concept, bad word.
right, you had the right idea. But we gotta make sure our terms are correct. Otherwise you'll fail exams. And
Of course, now I'm gonna remember preemption. 'Cause
Alright, find some page of memory that's really, not really in use, swap it out. So we need to consider algorithm and performance. Obviously, performance with operating systems. Hopefully you've seen that word a lot in operating system, but performance is vitally important.
So all of our memory spaces are gonna have a least recently used flag.
Good start. You want to teach this real quick?
No.
Okay. Same page may be brought into memory several times, so there could be it swapping to disk and coming back into memory. All right. To prevent overallocation of memory by modify page fault service. All right. Use dirty bit to reduce overhead of page transfers. Okay. Y'all familiar with dirty bits? All right. Great. So if it hasn't been modified, then it's not dirty, so it doesn't need to actually be written back to disk. But if it has been modified, just set a dirty bit. That means when you want to replace it, it does need to write back to disk first. So there, I explained dirty real fast. Page replacement completely separates logical memory and physical memory. Correct. Okay. I think they could have done a better picture here, but I'll show what's going on. Let's say that's trying to load M, and for some reason we'll say that M, that this whole thing is in use. What was over here was up here. So what happens is B, which was right here, aka right here, it needs to be written out to disk, and then M will be loaded back in here for process 1 to take. So notice it's evicting something from memory or process 2 and replacing it with something with process 1, so process 1 can continue running. Everyone good with this picture? Matt's always good with the picture. All right. So basic page replacement. Find a free frame. If there's a free frame, use it. If there's not, select a victim. Place the desired page into the newly free frame. Update the page, aka write the victim out to memory or to disk if you need to, and then make the new free frame free, and then restart the process. All right, great. Oh, good. Another picture of victim. That's right here. Okay, we select this guy as the victim. Swap it out to page. Change it to invalid in whatever previous page table was using it, because now it's invalid. You can't use it. Then you swap in the desired page, and then you reset the table with the valid flag turned on so that your process can reference it. Page replacement algorithms. All right, let me pause.